Can you hear okay in the back there? Is that good? Here, let me make the font a little bit bigger. Is that visible in the back now? Cool. Okay, thanks. So what I want to talk about today is something called dependent types. So dependent types are the basis of tools called proof assistants. How many people have used a proof assistant of some sort? So, lots of people. Okay. How many people have used them? Yeah. Okay. So what I want to do is to give a little bit of a taste of dependent types and to talk about kind of what dependent types do from a programming point of view that regular simple types like you might find in ML or Haskell or something like that don't do. And the example that I want to do to use this, so I started to make some slides for this talk and then decided that the slides I was making was basically showing you what interacting with a proof assistant looks like. And so then I decided that an easier way to do that would be to actually interact with a proof assistant. So we're just going to write a little bit of code today. So the thing I want to do is to talk about writing programs that, this example is going to be a type-safe printf function. It's inspired by a paper called Cayenne, a language with dependent types by Leonard Augustin. And so what I want to do is to start.
Leonard's actually here, not in this room, but
yeah. Yeah, Leonard's at ICFP this year. So yeah, I mean, that was the first paper I could find about this, but it's sort of one of the very standard examples of dependently typed programming. So it's the kind of thing you'll see different people doing in different languages. So broadly speaking, dependent types refer to types that can refer to programs. And the first question that comes up when you have something like that, types that refer to programs, is, well, what does it mean if the program prints to the screen or edits a file or something like that? So what people typically do is they look at all of their programs and they cut these programs down to just what's called the pure ones or the non-effectful ones or the total ones or something like that and allow dependency only on those. There's different ways to cut things down. You can encapsulate effects in different ways. There are dependently typed languages where the programs themselves are free to be effectful, but the well-typed ones will actually not have any effects. So those are computational type theories. In the style of Nuprol, you can have what's called benign effects, which is effects that you use behind the scenes that don't really matter. So think splay trees or something like that, where you're doing some effects, but it behaves purely behind the scenes. Okay, so I just wanted to broach that before we get to writing some code because it's going to be important for the code we write. Okay, so the first thing I want to do is to talk about a very simple dependent type. And to depend on something, we first need something to depend on. So we're going to start by having a type of what's called tags. And this is just like a data type. So I'm using the Agda proof assistant here, but you could do this in basically anything. This data type of tags is just a data type like you might have seen in ML or Haskell or something like that. So it's an inductive type. It's got constructors named unit, nat, string, list, and times. And the underscore syntax there for in Agda for the times is something that tells Agda that this thing will be used in an infix notation when you actually apply it. So if we're actually going to construct a value of this type, it'll look like nat times list string or something like that. But that's, just notation. Okay, so are we good on like what that data type is? I mean, you could write that in ML or Haskell or anything. Good? Okay, so now let's write a dependently typed function that processes these tags. What we're going to do,
John, what are the backticks?
That's just notation that I happen to have named the constructors backtick unit, backtick string, etc. just because otherwise backtick times would have collided with the actual times. So it's just notation, yeah. Okay, we'll see that. So what we're going to do is we're going to write a function that turns tags into actual types. Okay, and it should be pretty clear how this should go because the tags look like types, even though they're elements of a data type, like you might write a data type in ML or Haskell. And so we'll just turn them into the corresponding types. So that function will proceed by recursion over the tags, and we can get Agda to help out with setting up the form of that recursion by generating the cases for us. And then what we'll do is we'll just turn each tag into the corresponding agda type. Okay, so when we get to lists, right, so when we have the unit tag, that becomes the actual agda type with one thing in it. When we have the nat tag, that becomes the actual agda type of natural numbers, which are defined elsewhere. When we get to lists, what happens? List takes a tag as an argument. The list type takes a type as an argument. So what should we put in the hole here? Data of t. Right, we're defining a function recursively that traverses this syntax tree for a type and produces a tag. Okay, and then for the product type here, we'll turn it into the agda product of T1 and T2. Okay? Yeah.
I noticed that you have both type and set. What the difference?
Type is just my notation for types for today. Oh, did I have set somewhere?
Yeah, I noticed somewhere in one
Okay,
post.
well, yeah, so agda's just, whenever it says set, pretend it says type, which I find to be better notation than set for types. Good? Okay, so for example, the following is data for nat times list string, 5 comma the list with one thing in it, the string hi. Okay, and if we had put, I don't know, the number 7 or something there instead, then we'd get a type error because nat is different than string because, right, good? Okay, questions? Yeah.
I was expecting data called on the argument should return some kind of type.
Yeah.
So I was expecting the second line to be something like nat and string correspond to something a list, empty list.
Mm-hmm. That's what this is. This is a particular nat and a particular list of strings. Right, so an element of data nat is a nat together with, right, an element of data nat is a number. An element of data list of string is a list of strings. An element of the pair is 2 elements next to each other.
I'm confused by the signature of data. So it takes a tag and returns a type.
Yeah.
But I don't think 5 is a type.
No, so this, some data here, so here, this is a great question because this is kind of the crux of the matter. That right there is a tag. Data applied to that is a type. Some data has that type. Okay, right, this is the level mixing that's new if you're only used to like simply type programming. Yeah.
So I have a basic question about dependent type programming.
Uh-huh.
The dependent type programming is that you can convert value to types, right?
Yes.
So is all these values needs to be stated?
No, we'll see examples where the values are dynamic later in the talk if we get there.
Then how you're going to type it?
Yeah, yeah. Well, that's something I want to get to, but we'll see. Okay? Okay. So now the first thing I want to do now is to write a function that takes a tag along with data for that tag and produces a string. That is, for all of the tagged values that we defined so far, you can convert them to strings. So this is like an overloaded toString function that will work on all of these types. Okay? So how are we going to do this? We're going to do this by looking at what the different tags are and doing something different for each tag. So suppose the tag is unit, which is the type with one thing in it. We could convert that to a string by returning, I don't know, the string with the empty tuple in it or something like that. Suppose it's nat. How should we convert that number to a string? Well, it depends. Yeah. Well, I mean, yeah, like there is one, but I don't want to use it. I want to, yeah. Okay. So So how do we convert it to a string? If it's a number, then we can look and we can see if it's 0 or 1 plus a number, 0 or successor. Okay. Why can we do that? It's because when we're in the case of toString, where the tag is nat, the type of the data is data nat, which is nat, right? When we do a case analysis on the tag, we learn something about the type of the rest of the data. That's the key thing you can do with dependent types that you can't do without dependent types. You can learn something in each case of the function. Okay? So, since d is a number, we can ask, are you 0 or successor? We can serialize 0 as 0. We can serialize a successor as 1 plus toString of at nat of d, that is 1 plus the recursive call. Okay? If we're serializing a string, then it can just be the string itself, right? Notice that the way the code works varies, right? Here, when it's a string, we know that d is a string, so we can return it as a string. Good? Well, it depends what we want this to look like, right? Yeah, I mean, there's lots of different ways that you might serialize data depending on whether you're trying to be able to read it back in or present it to a person or something like that. Yeah, so, you know, the stuff on the right-hand side is kind of up for grabs. If it's a list, yeah.
So are we going to see like an actual number, like in base 10 notation, or is it going to be like 1 plus 1?
No, I mean, like, we could use write a function to do that, but since our built-in numbers are like unary natural numbers, I'm just going to serialize them in unary. Yeah, yeah.
How are you generating the code? Is it Agda or is it just Emacs?
It's Agda's Emacs mode. Yeah. So I'll post this stuff on my website, and you can like play with Agda sometime. I don't have time to like go through all the mechanics of Agda. I figured I'd just give you a taste for what it looks like to use it. Yeah. Okay. So if it's a list, similarly, we can, I don't know, turn nil into nil. And okay, so suppose the tag is list of t, and the data is x cons d. Then what do we have? The first element is data for t. So we can toString with t, the head of the list. And then we'll put something after that in the string. What should we put after that in the string? The recursive call with list of t and the tail of the list. Okay? And, you know, maybe we want to put a cons in the middle there or something like that, depending on what we want this to look like. And then for the product one, okay, this is getting a little repetitive. What do? toString the first half of the pair, and then concatenate that with toStringing the second half of the pair. Okay, good. Maybe we want a comma. I don't know. Yeah. Right. Like.
First and second significant?
It's just because they're record projections, and the Emacs mode colors record projections pink. Yeah. Okay. So the thing to, you know, like I wanted to kind of give you a flavor for what it feels like to type this stuff out. The thing to notice is that this code doesn't really have a simple type in ML or Haskell or something like that, like with just a basic simply typed lambda calculus kind of type system, because each type, each branch of the case uses D at a different type. And the way that's all coordinated is by knowing that the type of the data varies with the argument to the function as you case analyze. Okay, good?
Almost as good as programming in C.
Yeah, exactly. Right? I mean, the whole point of... Yeah. Yeah, I mean, so one of the things to, you know, notice about dependent types is that it's a way where by saying even more about the types, you can get closer to what code looks like if you have the types in your head, but don't express them in the program, right? You can play tricks that you would play in untyped languages. Okay. Thanks, Robbie. Okay, Next. All right, so let's skip running those examples. So what I wanted to get to, and yeah, we've got 15 minutes, so this will be good, is to talk about writing a printf function. So what I just did was to write a toString function where, okay, you supply the type of the thing by writing out a little code that looks like that, right? Nat cross list of string, and then I give you a nat and a list of string. Or nat, and then, if I'd said toString with string 1, then that wouldn't have worked. But because I said toString with int 1, or toString with nat 1, we're good. Okay? That doesn't exactly look like printf. What does printf look like? Have people used printf? Not very many people have used printf. More people have used proof assistance than printf. Okay. Good. Okay. So what printf looks like is you have a format string like dear %s, you signed up for %u talks today. I was thinking this is part of like the conference webpage that's, you can like star the talks and it'll tell you what your schedule is for the day on Researcher. Okay, so it's printing out that kind of message. The idea is the format string tells you both the text that gets printed out as well as the kind of types, number and types of arguments that go in the holes. So %s means I expect a string here. %u means I expect a number here. %l, %s is going to mean I expect a list of strings here. Okay, so this isn't exactly printf, but it's kind of inspired by it. And then what you supply is, well, you said a string, so you supply a string, a number, so you supply a number, and then a list of, you said a list of strings, so you've got a list of strings. Okay? And so the things we need to do to close the gap between the thing we just wrote and this printf function is, number one, we want the thing that's describing the types that are coming to actually be a string instead of to be one of these tag thingies that I made up. And number two, we're kind of mixing the text that gets wrapped around the arguments with the actual arguments itself. Okay? So we're going to do 2 steps to get that code. Okay, so the first thing is I preloaded us with a little helper function that, like, this is just straight simply typed code, no fancy dependent types going on here, that parses one of those little format strings off the front of a string, where string here means list of characters, and gives you back the tag corresponding to it. So if you see %s at the front, then the tag you got is string, and then it's returning the rest of the string after that. If you see %u at the string, then at the front, then it's returning nat and some stuff after that. If you see %l, then, well, we need to make a recursive call to figure out what it's supposed to be a list of. And then we return list of that and the remainder. And if we don't see any of those particular strings, then we just say, okay, stop, fail. Good? Questions on that before I move past it? Okay. So with that little helper function that just handles the gap between strings and tags, what I want to do is to write printf. And the first thing we need to do is to describe, given the format string, what the tag describing the arguments is. Okay? And one thing I should have introduced here is that this with notation, with ... bar that, just read that as case analysis or match or whatever syntax you're used to for that. That is, it's doing a case analysis on parse1 format of x's, and in the none case it returns none, in the sum case it returns sum. Okay. All right, so how should we decide? So here's an example for what I want args to do. When it's that string that we were talking about before, that should give back, oh, the arguments for that thing are supposed to be a string and a nat and a string list. Good? Okay, so how should we start args? Yeah. Let's parse one format from the front of S, which will either return sum of a format and the rest of the format string, or it will return none. Okay? If we got a format, then the format we want to return is that format and then the arguments for the rest, right? Because if we saw %s, %u, or something like that, we want to first grab the %s and then keep going with the recursive call. What if we get none? If we couldn't find a %s, a %u, or a %l at the front of the string, what should we do? Not quite, right? Think about the format string here. Yeah, you've got the idea. Think about the format string here, right, where it starts with the word dear. We need to pass by the things that aren't format strings because those don't contribute to the types of the arguments. Okay? So we can do that by case analyzing s and, okay. So there's an issue. Well, okay, let me first say, we can do that by case analyzing s, and if it's none, return unit, and otherwise pass by one character, okay? Because we'll skip the D, and then the E, and then the A, and then the R. Okay, so this is the right idea. If we try to load it, then Agda complains, termination checking failed. Remember that we said functions have to be total. Functions have to be effectless, right? One thing that Agda was doing for us behind the scenes here, all the way through, is checking that our functions terminated so that we knew that they were total. Okay? Why does termination checking fail here? It's because we start with args of s, and we make a recursive call on args of rest, where rest is the output of that helper function that I wrote for us that said, grab a few things from the front of the string, a %s or whatever, and then give back what's left over. Agda can't spot that whatever's left over is in fact smaller than the string we started with. So there are definitely ways to fix this, but the easiest one is to put in a directive that says, I know what I'm doing here, okay? So I'll do that since we only have a few minutes left to finish things. Yeah, I mean, I could have like inlined, if I just inlined parse format 1 into this function, it would notice it. I just wanted it at the outside because it'll be handy for the code we're going to write in a few minutes. Yeah, so, you know, when you're developing stuff and using these tools, one thing to definitely keep in mind is that sometimes you know what's going on better than the tool. And it's nice to go ahead and do your work and make sure that, you know, everything's going to come together before you go through the hard work of figuring out how to convince it that you're right. And so I'll post the version with the termination checking fix there. It's not much harder than this, but it's a little bit more complicated. Okay, so we good on args? All right, so to finish things off, the last task we have is to actually write our printf function. So how should our printf function go? Printf takes a string and the arguments for that string and gives you back a string. Well, if a function takes the arguments for s, and arguments for s was defined like that, then a good strategy is to follow the same pattern of definition that we used for arguments of s, so that in each case we learn what the arguments for s are. Okay? So if we do that, then we might say, okay, let's parse one format from s as the first thing we do. And if we get back sum of f and some rest, we'll do something. And if we get back none, then we'll do something else. Oops, sorry. Okay. So suppose we get back sum of f and a format. In that case, it means we found a little format gadget at the front of the string, which means that because we know we're in that case of args, we know that the args are data for that very format together with data for the rest, which is what will allow us to do. So how can we print stuff out? We can toString the first of A, right? Because A was a data with format F, and F is a format. Second, we can make a recursive call to printf, where we have the format string rest lining up with, I'll format it better, the second of the argument, right? The idea is, in this case, the description of the arguments that we computed by looking at that string was something that goes with the first format together with something that goes with the rest of the format string. So we can use the generic toString function that we wrote earlier in the lecture there and use a recursive call to printf on the rest of the format string there. Okay? So just to finish it off, what if we have none? Then we want to take a look at what the string is, because that's what args does. If it's the empty string, then, well, nothing to do there. What if it's a character that we blew past when we were computing the args, like the DAR in the word deer at the beginning? We'd better put that character in the result, and then we can make a recursive call with S and A. Okay? And this will have, if we don't promise that this is terminating, then this will have the same termination problem as the args function did and can be fixed in exactly the same way. Okay, so now I wrote a little wrapper here that works with strings instead of lists of characters. Right, so this is just wrapping it so that I can like type a literal string instead of a list of characters there. And so a test would be something like this. This is the example from before, where we had, dear someone, you signed up for talks something, you signed up for, oh, sorry, there's like a word that's duplicated here. Dear so-and-so, you signed up for some number of talks today, that and that. And then because of that, we're supposed to be able to apply this to a string, a number, and a list of strings. Okay? So if we give it a string, a number, and a list of strings, and a unit, which is just coming from the bottom-out base case of the args function there, then we get what we wanted. And if we had said, I don't know, a string or something there instead of a number, then we get a type error, right? The whole point here is that printf takes, I don't know how many arguments. It depends on what the format string is. It takes, I don't know what types of arguments. It depends on what the format string is. But we nonetheless get static type checking because we're reading in the format string at compile time, computing the types of the arguments, and making sure they line up. Okay? And so if we apply things appropriately like that, we get that. And then we can run it. And it says, fills in the values we provided in the right places. Dear Dan, you signed up for, well, that's how we decided to print numbers. So 2 talks today. And the talks were types of types and a taste of dependent types with however we decided to print strings. Okay? So down at the bottom of the file, the next thing, I'll post the file for you to look at if you want. Down at the bottom of the file, the next thing that you can look at is just how you would do all of this if you want to have a dynamically determined format string instead of a statically determined one. And the key idea is that what you do if you want to have a dynamically determined format string instead of a statically determined one is you need to do a dynamic check and dynamically check that the type of the data you provide is the same as the type the printf thing expects. But it's not the type of the data and the type it expects. It's the tag of the data and the tag it expects. where tag is just the data type that we defined at the beginning of the talk, okay? And you can write an equality function for that. It's just a data type. Use deriving equality if you're a Haskeller to get it, and then you get there. Okay, so that's a taste for how dependently typed programming works. Thank you.
One quick question?
Can these printf format string come from a file?
Yeah, so that's what I thought I probably wouldn't get to say it when, by the time you asked the question earlier in the talk. But so this version of printf, the dynamic one down here in the file, the format string could be read in from a file or whatever. It's just that when that happens, you need to do a dynamic runtime type check in order to make sure that the arguments you're providing are correct. So whereas the previous one statically failed the type checker when the arguments didn't match up, this one will have an return none or raise an exception at runtime when that happens. So I can tell you about this version after.